Hello and welcome to another edition of Light at Speed. In today's video I want to talk about the lumens a luminaire produces in total compared to how many actually might be used to illuminate your target. To do this, I first wanted to set the scene and have asked a friendly lighting designer to roleplay with me. This is a conversation I've had many times in the past, so do enjoy.
Hey Matt, how are you doing? Hey, I wonder if you can help. I've been looking at your data sheets for the Evo 16 and I can see that it only puts out 700 lumens?
Hey Chad, yes, that's right.
Well, I need 1,000 lumens.
Oh, okay, I understand. Well, we'll have a 1,000 lumen spotlight really soon. In fact, I got one of them out of the engineering office a few weeks ago.
Great!
But may I ask what you need the 1,000 lumen fitting for?
Sure. I have a museum actually here at the Cowboys Stadium, and I need a gorgeous fitting.
Box ticked.
To illuminate art.
Forgive me for being silly, Chad, but why is the lumen figure the most important one here?
Well, 1,000's what I need to light the art adequately.
Okay, so I imagine an uglier fitting produces 1,000 lumens, but it's got enough peak intensity for what you need?
Sure.
Well, forgive me again, but tell me how far away the art is from the light, how big the art is, and what are your intensity requirements for illumination?
Hey man, sure. It's 10 feet, so about 3 meters. The pieces are standard, portraits. They're about 65 centimeters high. I've actually got a 200 lux limit.
So in my quick head maths, you're going to need a 15-degree beam, and at 3 meters, a 700 lumen Evo 16 will have a peak intensity of 605 lux, which sounds like enough, doesn't it?
Oh, I see. Well, thank you for that.
Hey, no problem, Chad. Always happy to help.
Hey, Matt, one more thing. You want a job?
Gotta love Chad. I'm sure you already know that lumen output rating might not be the most important thing. And given that energy usage is becoming more important as each year goes by, wouldn't it be useful to understand how efficient a luminaire is at focusing the lumens its chip produces? But how do we quantify this? And what do we need to look for to learn more about the lights we use? First, let's go through some key terms and their meanings. What are lumens? Well, lumens are a measure of the total quantity of visible light emitted by a source. But even then, there are lumens from the LED chip, we'll call those chip lumens, and then there is the amount of lumens which actually make it out of the luminaire, which we will call fixture lumens. Remember, 99% of LEDs emit their light in a hemisphere, and in some cases that is what you might want. Cove lighting or floodlights, for example, are more suited to spreading the light everywhere. But when you want to focus that light energy into a beautiful beam, you will need a lens, a reflector, or even both. And these are never perfectly efficient. You may also have a snoot to reduce glare, and then the fixture lumens will be lower than the chip lumens. But how many of those fixture lumens end up in the specific beam width of the luminaire that you have chosen? Understanding how beam width is determined is also key here. The beam width that our industry uses is also known as the half power beam width, because the angle is determined by finding where the intensity of a beam is half that of its peak. It's not merely where the light is no longer emitted. So fixture lumens cannot tell you how much light energy coming out of a luminaire is focused into your selected beam angle, because there is almost always light spill beyond the beam angle's cone. This is very obvious when one looks at most reflector-based LED products, as they can appear to have a fried egg beam, but it's not isolated to them. So, we would like to get a grasp of how efficient a luminaire is at focusing the lumens emitted by an LED or any source into the beam width we want. Only then can we determine the effectiveness of a lens or reflector system. So to do this, I will need to make an assumption. We will call useful light the amount of energy inside the denoted beam width, using the half power point. Put another way, if we've got a 12-degree beam width luminaire, the useful light will be anything within the 12-degree beam. Anything outside we will say is wasted light. Sounds harsh, I know, but I believe it's the best way to demonstrate this. We should note, however, that a soft-edged beam is widely regarded as a benefit, and so the assumption here is more to show the principle where in reality a graduated edge would be more realistic. We will be testing a collimator lens against a reflector, and in both cases we'll be using the same LED chip, which outputs 1000 lumens. Both will have the same glare control for the test too. In this image, you can see from level, a collimator works to try and focus as much light as it can in the useful direction, and also how a reflector misses some rays which are wasted. First, let's take a look at the plot for the collimator, also known as a total internal reflection optic, or TIR. It shows a luminous intensity as a percentage against angle. As with most spotlight plots, the peak is in the center of the beam at 0 degrees. And we can see by the point we reach 20 degrees from the center in one direction, or 40 degrees full beam width, there is little to no light being recorded. Crucially, the half power point is just beyond the 12-degree full beam width, so we will use anything inside that as our useful area and anything outside as wasted. Next, we'll overlay the reflector's plot using the highest peak intensity as 100%. And straight away we can see that the peak intensity is far lower. In fact, it's 55% that of the collimator. And remember, both use the same LED chip emitting the same number of lumens. Again, the half power point is just beyond 12 degrees full width. But in this case, there is measurable light all the way out to 80 degrees full width, way past where the collimator's light dropped off. So using my assumption of light outside the half power point being wasted, there is much more wasted light with the reflector. So of the 1000 lumens the chip produces, how much as a percentage went into useful light and how much can be classed as wasted light? Now, I'm not an expert in photometry, nor am I a great mathematician. But light does fall on an area, and we need to account for that using the angle of the beam. But it also has a change in intensity across its angle, so we need to multiply the two together. Therefore, I think we need to work out the volume of the area under a graph when rotated in 360 degrees around its vertical axis. I have shaded the 2D areas of the plots for useful light in green and red for wasted light. I then import them into some CAD software, which lets me spin them into a 3D model and then gives me their volumes. Here are the 3D models for the collimator's useful light and the wasted light. So for the collimator, surprisingly, almost 50% of the lumens end up in the useful light beam and 50% are wasted. This may sound like it's really inefficient, but when we compare it to the reflector, it might start to look better. Here are the 3D models for the reflector's useful light and the wasted light. See how the useful light model is shorter and the wasted light model is wider than the collimator's. Maybe less surprising now is that only 27.7% of the lumens end up in the useful beam, which means over 72% of the lumens are wasted outside the beam. It must be said that if we repeated the test with wider beam angles, the amount of light that the reflector spills would drop. But I picked narrow beams because technically they are the most difficult ones to perfect. And it is with these narrow beams where both precision lighting and remote controlled lighting attempt to excel. So in conclusion then, if you want to illuminate a very wide area with lots of light, like with linear tape or floodlights, the more lumens the better. Because optics are more efficient the wider the beam angle. But when you want focused, precise, beautiful light, the quality of the optics play a much larger role. And in our test, the collimator fixture had almost twice the peak intensity of the reflector fixture, for the same number of lumens and the same amount of electrical energy. So next time Chad tells me the Evo 16 doesn't have enough lumens for his project, hopefully he means the peak intensity is not high enough at the beam width he wants, and hopefully he watched this video. Thank you so much for watching. I hope you enjoyed this video, and if you have any questions or comments, let me know down below or drop me an email. If you think the technique I used isn't quite right or you want to discuss it more, give me a call. Please be sure to like, share and subscribe, and I'll see you again soon. Bye bye.